Hello, everyone. Thank you all for coming. While we wait to just start, please fill out this giveaway form just to enter to win $200 in the GMAT or GRE tutoring and get a free MBA bootcamp spot. And I dropped the link in the chat as well. And then Marie can take it off.
Okay, ready to go now? I can do
Yeah,
that.
go for it.
I have to look at this slide. Okay, sorry, this is my slideshow. Okay. Um, Siri. Okay. Okay, this is about me. Sorry, this is the slideshow they present for me. So I'm going to be doing a lesson on integer properties. I do this thing called number caterpillars. So this is my QR code. Yes, and I forgot that I do have my promo code for this. So it's Marie Bursick spring 20, exactly like that. But you can find me on the Leland site. You can book me for an intro call, and then you can and we can discuss further. I am definitely, without a doubt, super booked already. I'm already starting to schedule people for who want to start in September. That I'm not saying I'm like waitlisted till September, but a lot of people are sort of planning. I'm finishing up a lot of people right now who are finishing or still working with people who are applying for round one. And really, if someone's starting from scratch right now, you're really pushing it for, if you're still thinking about round one, it's definitely possible. Nothing's not. I work with a lot of last minute things, but I don't love last minute. So I hope you just jump on things and and go faster and go faster. Okay. So let me see. Okay, let me take this away. And I don't know if there's anything really here. If anyone's joining this again, let me just show you one more thing. This is the $200 giveaway. People have been doing this in I was on something on Monday, so I know they're running that. And okay, anyway, let's get started. Okay, so okay, it starts off a little bit simple. I try to like ease you into this, and by the end, I'm going to show you some more advanced problems. So this lesson is my lesson on integer properties. I named it, it's like has something to do with number caterpillars. It's a thing that I made up when I taught middle school a long time ago, but it's the way I look at all numbers. And what I would like you guys to do is set up your notebooks however you want. But what I always ask my students to start over here and start listing the first prime numbers. The first 10 prime numbers. And when you get to the 10th prime number, drop it in the comments and, everyone else take a look. But people sort of fizzle out with prime numbers and they think that they stop around 11. And if you need a reminder, prime numbers are indivisible, or I think your teachers always said that they're divisible only by one and itself. So, yeah, go, take it away, start with prime numbers, and then I'm looking at the chat just to get some interaction. And I'm seeing, yes, these are answers I am looking for. Okay, good. Got enough. Let's get started. Okay. So your first prime number is not one, it is two. I'll explain why one doesn't work in a minute. And two is super important. Two is the celebrity prime number, I like to say. It's later on when I teach odds and evens and how to find odd numbers, but I always say that two is the contaminant. The other prime numbers are all odd. We have 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. 29 is the 10th one we should have. Okay, so basically, let me explain a little bit by like why one is not a prime number. What one is, sometimes people say one only has one factor and prime numbers all have two factors. And that is true. That is a quality of prime numbers versus one, but I wouldn't say that's exactly why I describe one as not being a prime number. Prime numbers are like elements on the periodic table, except there's an infinite number of prime numbers. They're indivisible particles that make up molecules, sort of like I used to call this number molecules a long time ago when I was just teaching SAT. And then I did that middle school stint and I changed it to number caterpillars. And I like the caterpillars thing because basically, like I talk about caterpillar cousins and like the bodies of the caterpillars and the metaphor changes. But let me just start with what I'm talking about. If you have a number like, well, first of all, like the water molecule H2O, okay? I believe that's like, when you learn about that, you learn it's a hydrogen and it's attached to, I'm sorry, an oxygen and it's attached to two hydrogens. And that's sort of how I think of a number like 12. When you do a number factor tree for 12, you start with 2, 6, and then 2 and 3. So 12 is 2 times 2 times 3. 2 times 2 times 3. And what we're saying is this is sort of something called the fundamental theorem of arithmetic. You don't need to know this, but the fundamental theorem basically says that every integer has a unique way of breaking down. And sort of, so 12 is 2 2s and a 3 and only 2 2s and a 3. And if you have 2 2s and a 3, it makes a 12. So it like works vice versa. So the idea behind the caterpillar is that I would sort of decorate them and it was like the caterpillar body. And I still use this thing because it's sort of like I'm trying to make something cute and personalized because it's going to get really scary pretty quickly. So anyway, let's do the caterpillars. Oh, and let me explain like why 1 isn't a caterpillar or isn't a prime number. Because if you think of the prime factorization of 12, it's 2 squared, 3 to the 1. And I could add a 1 here, another 1, another 1. It doesn't change the number. It's still a 12. So 1 is not like a building block number. It's not adding anything to it. And it wouldn't have I can't say there's a unique number or three ones or anything like that. So what I think of is 1 is really like the lack of prime numbers when there are no prime numbers. Another way that I describe this, and while we're, working, if you guys could do the caterpillars for 18 and 30, but I'll explain this over here, is when I ask someone like, is 48 divisible by 12? And I mean, the answer is obviously yes. And I try to say like, well, explain it. Like, explain to me why 48 is divisible by 12. What does that mean to you? And I know that most people just go 12 goes into 48 4 times. But the way I think about it is a little bit more like breaking 48 down. 48 is the caterpillar for it is, I mean, let's start with like 6 and 8, but it's 2 times 2 times 2 times 2 times 3. Or you can see 8 here, 6 here. And 12 is 2 times 2 times 3. And when I think of how a number, what it means to be an integer, or what, this number is going to result in an integer. If there's a question that says, if this is an integer, it means something like if 48 is divisible by 12, what it's also telling me is that the parts on the bottom, the prime numbers on the bottom are going to get canceled out or sort of absorbed by parts on the top. So that what is left behind is 2 times 2, and what's left behind here is 1, because you can't divide by 0, and we're not putting a 0 there. So 1 to me is really like it's something that stands in for the lack of prime numbers. And it is a factor of every single number. Okay, so 18. 18 is 2 times 3 times 3, and 30 is 2 times 3 times 5. Now, what I have my students do for these is by the end of my first lesson, and things that we're going to do today, I'm going to do divisibility rules. I am going to start with some questions that involve divisibility rules. And then I'm going to work towards factorials, some like difficult problems that you'll see in number properties. But I'm starting off with, like looking at this in an easy way. The other thing I tell my students, or one thing that I ask my students to do, like after this lesson, after I've taught the divisibility rules, is I ask them to caterpillar every single number between 2 and 100. And for anyone listening, this is a great exercise. It's a great exercise, but it helps you a lot with integer property problems and also with probability. But because they're more closely linked than most people realize. But this is sort of what the final product looks like. This is a student who had an iPad, and I always use hers as a model. So I always say like it starts from 2 and it goes from 2 to 100, now 1 to 100. I don't even want to see 1 on it. But she caterpillared every single number and like then she shaded them in, and all the 2s, every single thing here, just so you know, as you're looking, they're all prime numbers. Okay. And then if you have an unlimited number of colors, or if you use an iPad to make these things, you'll use 25 different colors. But usually with my students, I tell them like if they have 10 colors, it's pretty much good enough. The color that you use for 2, you're going to use the most, okay? And I actually have them hand count how many times the 2 appears, because it's relevant to when we start thinking about it in terms of factorials. But it's another way, like here's the other metaphor I use, that when we're doing like 100 factorial, we're stringing beads on a necklace. So 100 factorial is 2 times 2 times 5 times 5 times 3 times 3 times 11 times 2 times 7 times 7 times 97, and so on. Because a lot of factorial problems, you're going to be asked like, how many times does a certain number fit into 100 factorial? So for example, like how many times does 6 fit into 100 factorial? And 6 up here is made up of 2s and 3s. And ultimately you're counting the 2s and 3s. So this is a visual of it. And sometimes after you do it like through the long staking process of counting everything, it starts clicking when I teach the patterns of why they work. And sometimes I've had a lot of my students have taken other courses where they've learned tricks and they're not really sure why the tricks work. And I go into a more thorough explanation. So I think I might have been saying this before, but there are 25 different colors here, with like 97 being the 25th color, but that only gets used once. Any colors, there's 15 colors, there are 15 prime numbers under 50. And so I always say like the 15th color, which is 47, that 15th color is only going to be used twice. And like the 14th color is 43, that only gets used twice. 43 is going to be used here. And in 86, see, 2 times 43, 3 times 43 is off this screen. So basically this is something I always start with and something I'm going to probably refer to later today, but let's get back to the original lesson. Okay, so back to this. I also want to talk a little bit about the difference between a factor and a multiple, because I always say like factors fit inside. Factors are finite. Okay, factors of 12. 1 and 12. I always do the outside inside method. So like you're saying like 1 times 12, 2 times 6, 3 times 4. And there is nothing between 3 and 4. So I have all 6. So this is sort of saying 6 unique positive factors. The caterpillar later on will help me with bigger numbers. This one was sort of just simple, so I wanted to get into the idea of what a factor was. I will come back to doing harder ones. And the caterpillar, by the way, the number caterpillar, if I was just talking to a math teacher and explaining what I'm doing, I'm like, a number caterpillar is just saying the prime factorization of a number. But here, I'm going to color code these. So all the 2s, I'm going to make pink. All the 3s, let's say blue. And 5 will be yellow. Okay. Okay, so this is just going again over common terms. So factors of 12 are finite and they fit inside. Factors fit inside. All the numbers that fit inside 12, or all the integers, I should say. Multiples of 12 are infinite. Okay, multiples of 12 would be like 12 times 1, 12 times 2, 12 times 3, 4, 5. And this goes on for infinity. 0 technically counts as a multiple of any number, okay? Because a factor or a multiple of any number, a multiple of 6 is 6 times an integer. So you could even say -6, -12, but that's a technicality that really does not get tested on these tests. I know that there's a certain prep company that gets into all of this stuff, and it reminds me of like going to grad school. It's really out of scope. Like there's no way you're going to get questions up like that. But I do see those, I spend some time on Reddit and looking at what other people are posting, and there's just companies that I think are a little bit insane. But I mean, you learn a lot of math, they're cool, but it's not what's going to be on the test. Okay, so let me go over the concept of greatest common factor and lowest common multiple and remind people what these are, because they're usually switched. And I wanted to use this really easy example to explain something. The greatest common factor is squeezing this way. The lowest common multiple is squeezing this way. I think the reason I have to bring this up is because people hear greatest common factor and they think the number is great. And the lowest or least common multiple, they think it's a small number. And it's the flip. The greatest common factor is the greatest common fits inside. So the greatest thing that fits into all of these is 4. And the lowest common multiple is the smallest number that they all fit into, which is 48. And what I'm trying to illustrate is that 4, the greatest common factor, cannot be bigger than the smallest number, and the lowest common multiple cannot be smaller than the biggest number. I don't know if I said that correctly, but I hope this is helping. You don't ever look for a lowest common factor of anything, because the lowest common factor is just 1. And once someone said to me, what about 0? And I'm like, it's almost like getting theoretical. You don't look for a greatest common multiple, because a greatest common multiple is infinity. Okay. Like I could say all of these numbers fit into 48 million or 48 trillion. I could keep going with that. So we don't care about that. We're trying to find the smallest thing that they fit into, or the greatest thing that fits into all of them. And this is a way that I learned, a long time ago, actually in middle school, but it builds into much harder stuff. And it did help me really understand this, but I did contest math a lot in high school. So it's, I think that that's kind of like these strong skills helped me to translate all of this stuff into thinking about these tests, a lot of high school math or high school competition math, like American math competition type stuff. And the other thing is that, like, as anyone will tell you, this is like not a test really for people who are, if you're really good at calculus and you're an engineer, props, that's great. But this is really middle school math on steroids, on a lot of steroids. It's really, really hard stuff. There are hard questions about sort of simple concepts, and that could be reassuring and scaring at the same time. One thing is that you're really only reviewing a lot of things that you learned up until, like I always say, give me a really smart 6th grader over an engineer. And no disrespect to any engineers, but someone who like really understood everything they learned up until 6th grade, I could teach them all the other stuff pretty fast. Okay, so back here, the greatest common factor of 12, 18, and 30. When I'm looking at this, I'm thinking, I need to see the greatest common thing that fits inside. So they all have a single 2. I'm gonna put that here. They all have a single 3. So they all have a 2 and a 3. If this number were really 36 and it had another 3, if this number were really 90 and it had another 3, I would add another 3 and put that here too. The reason I'm saying that is because sometimes people don't realize that they can double up the same prime number, because you're saying the greatest amount of stuff that you see in all 3. That's what I'm really saying. Like, what could you collect from all 3? And in the bead, and if you're still like understanding, or if you're here for that bead analogy, what I'm saying is like, what are the greatest amount of beads that you could take from the 3 piles? Okay, I'm gonna undo this because I just have to use that for my lowest common multiple. So all of them have a 2, a pink 2, all of them have a blue 3. The greatest common factor is 6. Okay, moving on. Lowest common multiple. Over here, I put multiples of 12. Here's 60. It's 12 times 5. Here's 48, which is 2 times 2 times 2 times 3. Here's 36, 2 times 2 times 3 times 3. And what I'm trying to illustrate is if you are a multiple of 12, you must have the pieces that make 12 right here, okay? So when you're building a lowest common multiple, and I mean, I know that, again, there are tricks for this, but people get addicted to tricks, and I don't see it like that. When I'm building a multiple of 12, 18, and 30, I can start with any number, and sometimes I start with the longest one. All of my caterpillars are 3 bubbles long, so there's no longest one. but I sometimes call the lowest common multiple the mama caterpillar. Okay, because it's sort of like she needs to be a multiple of all three. And she's like sort of, I also say it's like a kangaroo and a poo. She's trying to be a multiple of all three, and she's going to put all of these beads or whatever in her papoose to hold them, but she doesn't want to carry any extra weight. So starting off with the 12, it's a 2 times a 2 times a 3. Okay, 12 is picked up. And then I look at 18, and 18, for her to be a multiple of 18, she needs to have 1 2, and that's taken care of. She needs to have 2 3s. There's 1 3 here. We're going to add a 3 to this. Okay, now the mama caterpillar is a multiple of 12 and 18. And there's overlap, but that's fine. And if we just take a minute here and focus, take a, reflection here, we've got 4 times 9, and 4 times 9 is 36. 36 is a multiple of 12. It is a multiple of 18. But it's not a multiple of 30, because 30 requires that you have at least 1 5. Okay, so now this mama caterpillar is a multiple of all three. And I want to talk a little bit about multiplying numbers. So this is something I'm always stressing with my students, is that when you multiply numbers together, really look first for 2s and 5s. This test, or both these tests, GMAT, GRE, they're always stressing that the concept of us working in a base 10 system. So, you counting tens and things like that. So it makes life easier if you can remember that, because 2 times 10 is 5. And then 2 times 3 times 3 is 18. So I have 18 times 10, and the lowest common multiple is 180. Okay. So that's the idea of a greatest common factor, lowest common multiple. I'm going to kick it in with harder numbers in a bit. Before I go into that though, and because I have 180 right here, let's say I asked you to find all the factors of 180. Okay, so what I would start off with is this caterpillar: 2 times 2 times 3 times 3 times 5. I'm going to put that right here. And I'm also going to point out that when this is buzzwords for number caterpillars. So if you hear words like factor, divisor, divisible, multiple, multiples, product of integers, what else? Oh, primes. But quite honestly, this also relates so much to roots and exponents. So a lot of problems like I had a student who recently said to me, like, everything's starting to, like, he's like, you're wearing off on me, because like I see the number 8 as 3 2s, not as 8. And I'm like, that's what I want. Like, when you see a caterpillar, the idea is that you start seeing patterns. And I always say that if these tests were like, if there was a word cloud that described these tests, the biggest word you're going to see, the biggest word I think, is factor. Maybe right next to it's pattern, but patterns and factors go hand in hand. So finding all the factors of 180. Okay, 180. Start with the easy ones. 2 and 90. 3 and 60. And right here, I usually stop and I ask students, does 4 go into 180? And I'm going to go with like the typical response that I get when I'm doing this with students. A lot of times, I see them go like, and they look over like that. And they're like, yeah, it does. And they do division. And what I'm trying to get you to do is not think like that. When I say that 4 goes into 180, let me look at this thing down here. I know 4 goes into 180 because right over here, I see 2 times 2. So I know that 4 goes into 180, and it goes into 180. Here's 2 times 2. It goes into 180 3 times 3 times 5 times. So 9 times 5, it goes in 45 times. Okay, so I'm not doing any division, and I don't want you to think about it like that anymore, because it is not really seeing the number for what it is. in 5 goes into 180. I think people know that just because it ends in 0, but how many times it goes in is you're going to hold the 5 away and multiply these pieces. So it goes in 4 times, 9 times. It goes in 36 times. And 6 goes into 180. Hopefully you just think, oh, 6 goes into 18 3 times. So 6 goes into 18 30 times. And then 7, I'm going to put aside a couple elements, okay? 7, 11, and 13. What colors am I going to use here? Prettier pink and okay. So when I think about 7, and I think, does 7 go into 180? No, it doesn't. Because sometimes people say, oh, like you can't multiply anything to be 7. Yeah, you can because 7's a prime number. So that color doesn't exist and it's not going to go in there. So 7's not a factor. 8 is 8 a factor? And 8's not a factor either, but 8's not a factor sort of for a different reason. And I want people to be able to distinguish. 8 is 3 2s. And when I'm teaching my students, I'm like, I don't want, like, if I ever ask students, like, how many 2s are in 8? I'm not really looking for the answer 4, like 2 times 4. I'm looking for the answer 2 times 2 times 2. So I think of 8 as 3 2s. Okay, 4 2s would be 16. But 8 doesn't go in because there's not enough 2s. So moving on, 9 goes in, 9 goes into 18 2 times, so it goes into 180 20 times. 10 goes in 18 times. 11 doesn't go in for the same reason 7 doesn't go in. It's a brand new color. That's not going to be in this original chain. 12 is 2 times 2 times 3. 12 goes in, and it goes in 3 times 5 times. It goes in 15 times. And then between 12 and 15, we have 13. 13's not in there, different color. 14 doesn't go in because 14 is 2 times 7. And while we have 2s, we don't have the color 7. So right now, these are all the factors of 180. Like, we don't have to keep climbing up. Sometimes people ask that, but notice just some things to observe, that they are spaced closely on this side and they're spaced widely over here, but we really have gotten every single one through this methodical way. Like, we just went through all of them. There are 18 positive, if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 times 2. There are 18 positive, unique factors of 180. A different question you might get, there are 3 unique prime numbers. Okay, but you never really get asked about the caterpillar or the prime factorization. The answer is never going to be something like 5. The caterpillar helps you find your other question, your answers. It doesn't, it's rarely asked about. I mean, I can think of one question that I've seen in the 8 years that I've done this. It has, like, asked about the length of a number. Okay, anyway, moving on. I, at this point, like to ask students just to test them, see if, like, they're understanding this concept, to find the greatest common factor and the lowest common multiple of 70, 60, and 96. So if you're just arriving and you're thinking about this, or you have no idea what I'm talking about, what I'd like you to do is the prime factorization, like factor trees for 72, 60, and 96. And just start there. And then we can find the greatest common factor and the lowest common multiple. And when you're done, I ask that you just write that you're done. Maybe not put the answers right away. I'll ask for people to put answers, but I know that sometimes in these sessions, people know a lot and can do everything really fast. And other sessions, people feel like I went too fast too. So I'm trying to just make it a little bit something that everyone can interact in. So anyway, yeah, start by doing the prime factorization. And I will say, like, for hints, okay, the greatest common factor is under 50, and the lowest common multiple is between 1,000 and 2,000. Right now I'm looking at the chat, so if anyone has any questions, even like, what are we doing? You know, just let me know. Um, Can I get a read on how people are doing? Just either if they are done or if they're confused. Okay, finished. I see some done people who are done. And if you are confused and you don't know what to do, I'm just asking, I would probably say the thing to start with is just do the prime factorization, like factor trees for all of these numbers so that you can follow along when we get ready. They're made up of just 2s and 3s and 5s. That's the only thing. So if you've got any 7s or 13s or any other prime number, that's incorrect. Okay, I'm going to move this along. 72, which is 8 times 9, is 2 times 2 times 2 times 3 times 3. 60 is 2 times 2 times 3 times 5. And 96 has 5 2s. 2, 2, 2, 2, 2, 3. Okay. So the greatest common factor, what do I see in all of them? Okay. If you have an answer for greatest common factor, please, you can put it in the chat now. Okay. Okay. Yes. Cool. Seeing some answers. Great. Okay. So if you're reading these other, I'm seeing these are correct. I see a lot of greatest common factors that are saying 12. That's what we're looking for. Okay. What that means is you are looking and you're seeing that every single one of these has 2 2s. The 60 only has 2 2s. The other ones have more. So 2 2s and a 3. I have 2 2s and a 3 here, and I have 2 2s and a 3 here. After I circle these boxes, the 60 only has a 5, and I don't have 5s in the other things. So this is the greatest amount of things that I can factor out of all of them. So the greatest common factor is 12. Okay. Lowest common multiple is usually where things get a little hairier. You're building a much bigger number that they all must fit into. So what do we have for the lowest common multiple? For the brave who got that, please let me know. Okay, good. Okay, I see 1440. That is correct. Okay, so basically, if you, a lot of people like, who've gone through other curricula, sometimes what they teach you is you do this like high, low with the exponents. You would need to have 5 2s for the 96 to fit in. So right off the bat, I'm going to have 2 times 2 times 2 times 2 times 2. That's for the 96, for the 96 to even fit into it. Now the 96 also needs a 3. Okay, so right there, 72 needs 3 2s. I have that covered. I need an extra 3. So now 72 is taken care of. And 60 has all the 2s and the 3, and it needs a 5. Okay. And what I would recommend is I'd still say, okay, I'm going to take a 2 and a 5, and that's 10. And I've got 2 to the 4th power times 3 squared. This is 16 times 9, and then times 10 at the very end. And 16 times 9, I'm going to also teach like double, how I do double digit multiplication, but well, let me just teach that now. So if I were doing something like 27 times 31, I tell people this is sometimes called the area method, but I take 27 and I change it to 20 plus 7. And 31, I'm going to change that to 30 plus 1. And then I'm going to go 30 times 20 is 600. 30 times 7 is 210. 20 times 1 is 20. And 1 times 7 is 7. And I do this also because like for the second lesson, I usually teaching people about a lot of units problems. And anytime you have a number like 27 times 31, right from the very beginning, I would know if I was going quickly on a test that the number has to end in a 7 because 7 times 1 is 7. But the units digit of any number comes from the units digit times the units digit. Because as you can see here, all the other numbers are going to be multiples of 10. So I'm going to add this all up. Let me finish this problem before I go to 16 times 9. So this right here is 810. Here, this is 27. You can do it in different ways. Usually I go diagonally, but it depends on the number I'm working with. 837. I say that because if I were doing 9 times 16, I do this more in my head. But I'm saying like it's 9 times 10, which is 90, 9 times 6, which is 54. And I add that together, I have 1440, put the 0 on. So lowest common multiple, 1440, those who put that, yes, very good, okay? Sometimes people use it just by counting exponents. That's fine too, but this is just a visual and I like to see it all out. And when I do it a little bit faster, I don't think that I'm always thinking about this, but it's because I see it like this. So it's not that I'm really using all the tricks. It's sort of like after you see it like this, you just sort of understand it more innately. And then hopefully, you get better with this. Okay, so I'm going to go through divisibility rules and then I'm going to do a follow-up problem. And I'm not going to go through all the divisibility rules, but I'm going to go through most of the ones you should know. And again, I'm going to say something. I learned this stuff in 7th grade and it stayed with me forever because I wasn't allowed to use a calculator in my high school. So it helps. The reason I make such a big deal about this lesson being my first lesson, and a lot of different curricula do different things where they do algebra first or other skills. But the reason this is so important to me is because everything comes from this. Every single time you have to reduce a fraction or do division, you have to be able to look at these pieces and see like a couple moves ahead. And getting really familiar with the numbers under 100 is a lot. I mean, knowing the numbers under 100, there's a reason I stop at 100. It's not just arbitrary. There is something about some of the numbers under 100, and I go into detail in my lessons about this, but well, and I'm going to probably spill some of this too. So rules of divisibility. Okay, so just starting off so you understand what we're talking about, you know that 2 goes into a number when the number is even. 5 goes into a number if the number ends in 0 or 5, okay? And I know you guys know that a number, when a 10 goes into a number, if the number ends in 0. So I'm not going to write those, but 2 and 5, I always start with those. These are the most important ones. The reason you know them is because we work in a base 10 system, and because they're so, they are the most important numbers because they really sort of like they lead to zeros. There's a lot of questions that ask about trailing zeros, and it's about base 10 system stuff. Okay, the next most important rule that everyone should know, and I don't know how people get their life without knowing it, is the 3 trick. So to know if 3 goes into a number, you sum up the digits, but the sum, here, let me write this. The sum of the digits is divisible by 3, okay? And I'm gonna demonstrate this in a minute, but let me do the 9 one as well, okay? Because they're so alike. And if you think about why they're alike, it's because 3, that's the caterpillar, and 9, the caterpillar is 3 times 3. So they're obviously very closely related numbers, okay? So the trick for 9 is that the sum of the digits is divisible by 9, okay? The sum of the digits is divisible by 9. This is the 3 and the 9 trick. The 3 is super important because, first of all, looking at this caterpillar chart, where did I go with that? Looking at my student's caterpillar chart, let's point out the fact that 3 is in every third number, okay? 3, 6, 9, 12, 15, 18, which is missing, 21. It's in every third number. So you already have a 33% chance that your number is going to be divisible. But what's good about it is it works for what I call like weird looking odd numbers, numbers that you're like, I think that number's prime. And a good example is this problem, okay? How many digits, I'm sorry, how many integers between 50 and 70 are prime? Okay. And because I'm talking to myself basically, I'm gonna kind of illustrate how I would treat this. First of all prime numbers are odd, every single one except for 2, and 2 is not in this range, so I'm just gonna write out all the odd ones. 51, 53, 55, 57, 59, 61, 63, 65, 67, 69. Okay, so right away, I know that 55 and 65 are definitely not prime because they are end in 5. They're definitely divisible by 5. Those 2 are out. Hopefully you're looking at this and you're thinking 63 is 7 times 9. I know that one. But even if you don't, I'll remind you the 9 trick, okay? Or the 3 trick, but 6 plus 3 is 9, and 9 is both divisible by 9 and by 3. So 63 is 3 times 3 times 7. That's its caterpillar when you do your caterpillars for that, but 63 is out, okay? Now the rest of these I would call weird looking odd numbers. Okay, I'm not really sure. They definitely could be prime. A lot of people think they're prime, but this is where the trick comes in. So 5 plus 1. 5 plus 1 is 6, and 6 is divisible by 3. So 51 is not prime. I'm going to put it over here. We can talk about long division in a bit. 5 plus 3 is 8. 8 is not divisible by 3. So since it's not divisible by 3, I guarantee it's prime. 5 plus 7 is 12. 12 is divisible by 3. Since it's divisible by 3, it is not prime. 5 plus 9 is 14. 14 is not divisible by 3. That's a prime number. 61. 61 is, when you add that together, you get 7. 7 is not divisible by 3. That's prime. And 67, add that together, you get 13. 13 is not divisible by 3. That's prime. And then 69, add those two digits together, you get 15. 15 is divisible. Why is it that we don't check 7 divisibles again? Okay, I'll let you know in a second. I'll answer that question. Okay, so first of all, 6 plus 9 is 15. 15 is divisible by 3. And I'm sorry, 15 is divisible by 3, so I know that this is divisible by 3. And then I'm going to go through these later. Okay, so first of all, let me just say something about what I call like weird looking, this trick. When I say this trick works for all weird looking prime numbers. And when I say weird looking prime numbers, I'm not talking about things like 77 or 33, because I think that you should know that those are divisible by 11. Okay, under 100. I'm talking about the numbers under 100. 99. Okay. But 55, obviously. So I don't call these weird looking prime numbers. The other ones I don't call weird looking prime numbers are multiples of 7. I would hope that you would know that 7 times 7 is 49. And what else would be under there? They have to be 7 times any prime number. But that brings up a very important part. There is one number, and I always tell my students, it's my favorite number, it's my favorite number. I make a big deal about it, so I want them to remember. There's one number that slips under the 100 rate, under the 100 cutoff line that the 3 trick does not work for. And the tests love this number. Okay, it is the number 91. Okay, 91 is the only number that when you look at that and you go 9 plus 1, that definitely looks like it's probably prime. And let me do the 3 trick. 9 plus 1 is 10. 10 is not divisible by 3, must be prime, but it's not. 71 is 7 times 13. So if it helps you remember, think it's the lucky number times the unlucky number, like whatever. To me, they're both kind of crappy. But I don't know if this question is, there is a rule for, there's a rule for every single number. Some of them just might take like, 5, like what I mean is there's a rule to figure out if a number is divisible by 7. We don't do it because I used to teach it about like 4 or 5 years ago. And then I was just like, the only reason I need it is for 91. And it's kind of a dumb rule. And I think that I want to de-emphasize it and not, like you can look up anything. You could look up how to tell if a number is divisible by 13. I have no idea, but there's definitely like some system that you could use to figure it out. How to tell if a number is divisible by 43. There is always some way to do any number, but there are only some that are actually important enough for this test and are like vital for this test, the GMAT, the GRE, and they're not, I call it like the edges of the universe. If I teach you this trick, you should know it because it's not outside the edges of the universe. I didn't learn all of these tricks in, say, 7th grade. There's 2 tricks that I know as a GMAT teacher that were outside of my 7th grade universe. But right now, when I say like, I'm not checking these things for 7 because I look at these and I know that they're, 63 was the one that I knew that was divisible by 7. Okay, so let me keep going with this. And if you have a question that I haven't answered, let me get through that. But I just want to, keep on track for a minute. Okay, and I also want to get back to doing long division here. Okay, so then I always tell my students the other thing about the 3 and the 9 trick is that they're magic. Okay, like I don't want to explain or explore or, either one why they work, but they work and they're great. Okay. They're going to work for every single number that you're like these. Okay. These weirdos. Okay. Another one's 87. Okay. 93 is sort of another one, but hopefully that looks a little bit more divisible by 3. And what they are, when we explore them, is you're going to see they're 3 times another prime number that you're like, you don't know your multiplication tables of the ones that we talked about earlier. You don't know your multiplication tables of 17 or 19 or 23 or 37. 31. You don't know your multiplication tables of those. That's why they can fool you. But again, the 3 trick, most important thing. When I'm a high school teacher and I'm teaching like my students trigonometry or when I was a high school teacher in my past life, and I did like trigonometry and calc, my students are allowed to use calculators, but sometimes they don't reduce as much as they're supposed to because they get lazy. And I tell them like, I have one answer key and I'm not going to try to investigate if your really big fraction is not the same thing as mine. So the 3 trick is something that I make sure everyone knows just so they can have a quick glance and, I mean, their calculators do a lot of the work. But, even then, sometimes I don't get the answer that I need. Okay, so 4 trick. Okay, 4 trick is not magic. I can explain it, but first let me tell you what it is. The last 2 digits are a multiple of 4. Okay, now it's not the 3 and the 9 trick. You are not adding them together. Let me demonstrate. 2,732. Okay, here are the last 2 digits. 32. I'm not saying 3 plus 2. I'm not dividing each one. I'm just saying I'm asking, is 32 a multiple of 4? And hopefully you're like, yeah, it is. It's 4 times 8. And that means if the last 2 digits are a multiple of 4, then the whole number is definitely a multiple of 4 or divisible by 4. I can use those words interchangeably, okay? And the reason for this is 4 goes into 100, okay? 100 divided by 4 is 25. 100 divided by 4, 25. I don't know how you want to think about that, but like if I'm talking about money, 100 cents divided by 4 is 25 cents, okay? 4 quarters in a dollar, okay? That is a number that you should know backwards and forwards. So when I look at a number like this, it's really the same thing as 2,700 plus 32. And I know 4 goes into 100, so I know 4 goes into any multiple of 100, so 4 is definitely going in this. Does 4 go into the leftovers? And it does, and that is why this works. So sometimes people say, oh, it's like the last 2 numbers are 0, 0. I'm like, yeah, 0, 0, because 4 goes into any multiple of 100. The 8 trick, which I feel like I have to teach because I teach with fractions, but I've never used it ever, is that the last 3 digits are a multiple of 8. So you would take a number like 20 is this number. 8 does not go into 100. 100 divided by 8 is 12.5. 1,000 divided by 8 is 125. Okay, I usually, even with my students, go, I don't feel like teaching 8 because you're never going to use it. 6 I do in a different color. 6 is, again, this is something I did do in 7th grade. So I only say this because I want you guys to realize that these things are not crazy hard. And they're vital. Okay, they're vital. And they're like almost, I shouldn't say almost, they are as important as learning your multiplication tables, because you need to be able to quickly look at numbers. There are times when I have something like, like a thing that's like 7 to the 214, and I need you to figure out the remainder when this number, when 214 is divided by 2. Sorry. If I ask what's the remainder when 214 is divided by 4, and anyone who's studied this and like knows the patterns and remainders, this is why it's important, because you could go like, well, 14, when that's divided by 4, it has a remainder of 2. And just because you don't even look at the, this number at all, you just care about that. So the 4 trick is like vital for everything we do. So is the 3 trick. So is 3 trick, 9 trick, obviously the 5 and the 2, a little bit more common. But the 6 trick is not so, here's what's going on with the 6 trick. The 6 trick is that here's a caterpillar for 6, 2 times 3. So the 6 trick is really when you're asking if something is divisible by 6, you're asking, is that number divisible by 2? In other words, is the number even? And is that number divisible by 3? Okay, so look at the number 1,002. Okay, 1,002, 1,002. Okay, 1,002 is even, so I know it's divisible by 2. If I add up all the digits, 1 plus 0 plus 0 plus 2, I get 3. 3 is divisible by 3, obviously. So this number has to be divisible by 6. And when I do long division, this is the way I do long division. I don't do it the traditional way that we learned, but it sort of borrows from this. I think a lot of people would go 6 and put a 1 up here. I don't do that. I just go, okay, like 6 goes into 600 100 times. And then I subtract, and then I have 402. And I think 6 goes into 402. It's sort of, again, the old way, like you might go 6 goes into 40, but you can do this, in the old traditional way, if you make one mistake, the whole thing's shot. This way, if I'm going to try to do this wrong just to show you. I know that 6 goes into the number 30, which is not the biggest number under 40, but I know it goes into 300. And I know that 6 goes into 350 times. And then I shave away and I've got 102. Now, if you're fancy and you know that 6 goes into 90, that'd be great, but we're not going there. 6, I know, goes into 60. And it goes in that 10 times, and then subtract 42. And again, I'm not going to be fancy. And I go, oh, I know that 6 goes into 30 and it goes in 5 times, and then 12, and then 6 goes into 12 2 times, and I'm done. And I add this up, and I took 2 more steps than are necessary, but I still get to, this is 160, 167. So I just found out that 1,002 is 6 times 167. And then 6 is 2 times 3. And 167, I'm going to show you in a minute how I can prove that that is a prime number. Okay. I'm going to teach, I wasn't going to do this, but I'm going to teach the 11 trick. The 11 trick is, this is the one that I learned when I was a GMAT teacher. I did not know this in all my years of contest math, but it's a good trick, and it's not outside the edges of the universe. You should know it. In my first lesson that I teach, it comes up like 3 different times. So 11. So with 11, you alternate positive and negative signs on each digit. Then you sum things together, and then you check if the result is a multiple of 11. But if you were still here in the beginning and you heard me say this, 0 is a multiple of every number, and 0 counts because it's almost always 0. Not always, but almost always. Okay, so I'm going to erase some of this stuff up here so I have room, and I want to get back to this problem. Oh, you know what? Let me erase over here. I'll come back to those randos that I need to do. Okay, so here's the 11 trick. Let's just start with ones we know. You guys know that 77 is a multiple of 11. This is what I do. You go positive, negative. That's what I mean by alternate the signs. Then I add that together. 7 minus 7 is 0. Okay, that's a multiple of 11. That's how the trick works. Okay. 187 plus minus plus. I am going to go 1 plus 7. It's 8. 8 minus 8, 0. Okay. So that just tells me that 11 goes into it. It doesn't tell me how many times. Now I'm going to go 187 divided by 11. Again, I don't really put anything up here, but if you kind of remember the old way, you would go like this. And all I'm asking you to do is go, like you would have put a 1 here. Now just put a 1 here, put a 0, put a 0 here. And you're saying 11 times 10 is 110. Now I'm going to subtract, and 77. And you'd go, 11 goes into that 7 times. So 7 over here, and like it went in 10 times to get to. So what I'm doing is, in the beginning, when I first, I always used to do this in my head with 2-digit numbers. If I was doing 91 divided by 7, I could do this. And I was shown this in grad school. My professor taught like the elementary school teachers how to teach math. And he showed us this way. And instantly I was like, oh, this makes so much sense because this is kind of how I did this. So all the other teachers like, this is how we're going to teach this now. And I realized that I always say, like, I got to teach 100% of my students how to do long division correctly. Not only because, sometimes people are like, I'm going to do it my way. But the thing is, this makes you go so much faster if you're just trying to find a remainder, because I don't count how many times I just go a lot faster and I just shave away. So trust me, it is a much better way. And I've had students who fight me on this. And then by the 8th lesson, they're like, I should have just given up and done this earlier. But anyway, back here, 11 goes into 187, 17 times. That's what I'm doing. Okay. Now, okay. The reason I did it is because I want to talk about this number and how to prove that 167, or how to investigate if it's prime or not. So 167, what I would think about is I look at that number, and the first thing I'm thinking is it's a weird looking odd number. Is it divisible by 3? 1, 6, and 7. When I add these digits together, I get 14. Okay. And 14 is not divisible by 3. So that's not going to work. So then I think like 169, okay, is 167 is very close to 169, or I think of like, what's a multiple that I know that's close to 167? And if you want to do 170, that would work too, okay? I'll put 170 up here. 170 is 17 times 2 times 5, okay? And this is 13 times 13. So 169 works a little bit better, but 170, I could use this reasoning too. Let me start with 169 because I'm just more familiar using this. But if 167 is not prime, then what you're saying is that it has at least 2 bubbles, because prime numbers, all the prime numbers, I put this over here. All the prime numbers you see are the ones that only have one circle: 17, 19, 61, 67, 71, 97. You know, these are the prime numbers. If it's not a prime number, then it has at least 2. And one logical thing is that if like 13 times 13 is 169, then 167, if it's not prime, has to have at least one prime number under 13. Like it could be 11 times 17, hypothetically, or something like that. But it couldn't be like 17 times 19, because those two numbers are bigger than 13. So it would max out. So what I have to do is really investigate all the prime numbers under 13. 2, 3, 5, 7, 11. These are all the prime numbers under 13. And I know that 167 is not even. I know it's not divisible by 5. I just did the 3 trick. That didn't work. So now I'm going to use the 11 trick. And 1 plus 1. Okay, if you don't remember the 11 trick, or if I didn't explain it clearly enough, is 1. Okay, plus minus plus. Sometimes people go, can I start with a negative? And I'm like, yeah, you know, if you want to be, if you want to be difficult, no, just kidding. But if you want to do some switch it up, it doesn't make any difference. It usually ends up being 0. It might end up being negative 11, but negative, I mean, they're rare, but if negative 11 counts as a multiple of 11, if you switch it up. Okay. So anyway, back here, I'm going to have 8 minus 2. Sorry, 8 minus 6 is equal to 2. And 2 is not a multiple of 11. So 167 is not a multiple of 11. And now the 7 trick, or not the 7 trick, but I have to investigate 7. And this is what I mean by why I like doing it this way instead. 167, I would think 7 goes into 140. And I don't really care how many times. Okay, I'm not writing this. And then 27. 7 doesn't go into 27. I mean, it goes into 21, 6 left over. That's enough for me to know that 7 does not go in. And again, this is a little bit what I'm emphasizing. Like, I don't need to count how many times or write that stuff on top. I just know 7 doesn't go into this number, because 7 goes into 140 and 7 does not go into 27. That's basically what I did. Okay, it goes in here, but it does not go in here. So since there are no prime numbers under 13, and I know that this number is not 13 times 17 because it's too close to this one, I know for sure that's a prime number. And this is the prime factorization of 1002. Okay, that's one thing that I wanted to show the 11 trick for. Okay, now I have something that relates to all of this, a problem for you. Okay, and the rules of divisibility: 2, 5, 3, 9, 4, 8, 6, and 11. But hopefully you remember more than just the 2, the 5, the 3. Okay, but you need to know more than the 2, the 5, the 3 for the next trick. The next problem, I mean. Okay, so which of the following numbers is divisible by 36? Okay, and I'm going to give you a little hint here, but I threw that word divisible up. So this definitely has to do with caterpillars, and obviously with what we just learned, because I want that to be. Here are my answer choices: 5,232, 5,000, 5,742, 5,244, 5,436, and 5,130. Okay. So take a minute to think about this. When you're not doing long division, okay, every time you do a problem, and I granted, if you're taking the GRE, I know you're like, I could use a calculator, but I don't want you to be thinking like that. Okay. I want you to be thinking, I got a caterpillar or something. We're definitely using the things I just taught you, the rules in some way. And if you do this problem and you think, a lot of times people just right off the bat, like shoot out an answer and they're like, I did these tricks and this one came out. I'm like, check all of them. There's only one right answer, is what I'm saying. Yeah, there's only one right answer. There's only one right answer. And I'm going to say these numbers, okay, because people sometimes complain that I write my 4 is weird, but this is 5,742. Okay, 5,000, this is 5,232, this is 5,742, 5,244, 5,436, and 5,130. And oh, I know what I was saying. If you are like, I could brute force this and do this all with long division, yeah, of course, but you don't want to do that because someone's doing this problem in 20 seconds. And you want to figure out what that way is. What's like the clever way to do it? Sometimes I'm like, what's the cute way to do it? Sometimes you're desperate, you do it the long way, but don't ever jump to any assumptions. That's really the heart, the thing that you want to stay away from, jumping to assumptions that like I taught you something and it's going to work for everything. I would tell you, I'm going to tell you this. These are the rules of divisibility that we just did. 2, 3, 4, 5, 6, 7. We're going to skip 8 because again, I'm not a huge fan. 9, 10, and 11. Okay. And if you want to know, okay, Elliot, I'm going to straight up tell you that's what I did the very first time. Okay. I checked for 6 and I like what you're thinking. If you're right to think that 36 is divisible by 6 times 6. And so you might check for 6, but I'm going to take some, if I would like you guys to check these numbers for 6 and something's going to come up. Okay. Okay. Yeah. See, 36 is 2 times 2 times 3 times 3. And if you check all these numbers, they're all divisible by 2. And if I sum them up, I'm going to show you some other things. Okay, when I sum up these, and I look for things to add up to 10. So when I look at this number, sometimes I see people go 5 plus 2, and I think this is 10 plus 2, and that's 12. And that's divisible by 3. And this number right here is 12 plus 6, that's 18. That's divisible by 3. This is 10 plus 5, 15, also divisible by 3. And I have 9 plus 9, which is 18, also divisible by 3. And this number is 9. So if you apply the 6 trick, all of these numbers are divisible by 6, okay? So the 6 trick, remember, is a combination of the 2 and the 3. And then you think this question didn't ask me if it was divisible by 6. It said 36. Why would 36 be different than 6? And what other tricks should I use? And Colin, I think, would say, yeah. Ali said I would start with 9 because it gives you fewer options than 4. But honestly, I'd almost reverse that because the 4 trick's a little bit easier. So I would just look here and I'd be like, yeah, that's divisible by 4. Because a 4 has to fit into it and a 9 has to fit into it. Remember when I did the 180 and I spaced them all out? Like I know 4 has to go into it. So 4 has to go into it. 4 goes into this number. 4 does not go into this number. 4 goes into this number. 4 goes into this number. 4 does not go into this number. So I've eliminated 2 choices. Now, then 9 has to go into the number. 9 does not go into 12. 9 does not go into 15. So these are out, and this is my winner, okay? So people who said D and use the 4 trick and the 9 trick, those are great. The 6 trick is just not good enough because it's not like mutually exclusive, and you don't want to divide all these numbers by 6 and then do it again. But what's going on here in this number is that basically if I caterpillared 5,232, I'm gonna make this clear. There will be 2 2s. I know there's actually another one, but I don't get into that, okay? But I know there are 2 2s and I know there's a 3. But the problem is there's maximum 1 3. Okay, there's maximum 1 3. This number was divisible by 9. And it definitely has 2 3s, but it has a maximum of 1 2. There are no more 2s in this chain, in this caterpillar. This number was divisible by 1 3, so it only has 1 3. It doesn't have 2. You're not going to find them in other places. It has 2 2s. So A was divisible by 12, B was divisible by 18, C is divisible by 12. This one, what did I make this one? This one was divisible by 2 3s and a 2. This one's divisible by 18. This is the only one that has 2 2s and 2 3s at the same time. Again, I will say that this number, this one I do know, I'm like just looking at it because I am kind of using the A trick and cheating when I said I don't even use it, but this one I think, I'm pretty sure it has another 2 in here. Yeah. Okay. And sorry, I'm thinking. But it could have more 2s, but I know it maxes out at 1 3. I know this maxes out at 1 2, maxes out at 1 3. So that's the point that I'm making. There are other ways that you could, if you get a problem that says what's divisible by 18, 3 times 3 times 2, you would do the 9 trick. You check and see if that number's even, okay? So even though I taught you that 6 trick and I put it in a different color, because it's kind of showing you it's nothing new, and then you want mutually exclusive tricks. And sometimes, like I have this really, really hard problem. It's a probability problem, a combinations problem, and I can't remember the answer choices, but let me just think. There's something like this, like 4 1 2. That's one of the, I think, good answers. 4 1 2 5, and then there's like 4 2 2 5. I don't know what else we have here. Like I'm just gonna make some random stuff up. 4 3 7 D, and I don't know, 4 2 7. Sorry, 7 5. We change this one. I know it made sense. Okay, whatever. Let me just put this. Let me see which one I want. All right. Okay. So there's a problem and it's very difficult. And most of my students realize that like one of the numbers is 15 and the other number is 5, and they can never figure out the third one. And I was like, okay, but let's start with what we have. We know that this number is 5 times 3 times 5. So the answer, and without a doubt, because the problem has to do with like combinations and permutations, this is definitely going to be an integer. So you know that the number has to be divisible by 25 and 3. And all of these are divisible by 25. So that didn't help too much. You can see that these could all be like, this could be money, $42, $42.25. That's how I know it's all divisible by 25. But let's look and see how many of these numbers are divisible by 3. And this one is not, because 9 plus 4 is not going to be a multiple of 3. And this one is not. Okay, that's 9 plus 2, that's 11. That's not divisible by 3. And I had to make one of these work. This one still works. And let's see, what did I make here? 12 plus 6. This one works. In the real problem, I can't remember the answers, but there was only 2 that worked. And I was like, you know what? Maybe you just never get it. But can you be a good guesser and just be like 50-50 chance, pick one, move on. Okay. So that's, like I sometimes tell my students, like, don't try to always be right. Just try to really not pick a wrong answer. And if you play that game, you can do really, really well. So, okay, let me see. I was going to talk a little bit about, I don't know if you guys are like, bored to tears here and want me to finish up. but I was going to talk a little bit about factorials, and I'm going to do just like some simple problems. There are problems that are much harder that will say something like, if, here, I'll just like, if, let's say something like 1,000 factorial is divided by 10 to the n. If this number is an integer, what is the greatest value of integer? Maybe 10 wasn't a great one to do. No, that would work. Of integer n, okay? Now, if you guys already know how to do this, fine, you can throw in your answer, but I'm not really going to be explaining this problem. I'm going to do an easier one and just show you how I could build up eventually. And there's a trick that comes with this. But first of all, let's talk about, like, sometimes when I'm teaching my students problem solving, I talk about, like, first you got to understand the question. So sometimes you want to just use an easier one. Let's say I said, like, if 12 factorial were divisible by 3 to the n, okay? How many times could 3 go into this, okay? You're allowed to use a calculator for the GRE, not for the GMAT, or I think in the GMAT, which I haven't been doing for a while, but it's like on Data Insights, you get one. But I'm going to say something. You do not want to use a calculator. You will use it maybe once, maybe twice, but really you have to, like, a lot of people are like, yeah, you get to use a calculator. And I'm like, how many times have you typed in an internet password incorrectly? I can do everything faster. I mean, like, your fat fingers get in the way. So it's like a false crutch. It's actually going to screw you up if you think that you're going to, do well with a calculator. So I've had students who are like, I didn't really like learn, your fraction to decimals. I use the calculator. They don't end up succeeding. They do that. Okay. I don't, want to, being a giant, I told you so. But let's look at 12 factorial. Okay. Let me get back here. So I'm going to look at this caterpillar chart. Okay. So when I think of 12 factorial, what I'm thinking of is here's my beaded necklace. Okay. I'm stringing along a bunch of beads. I don't think of it as 12 times 11. And if you don't know what factorials are, that's 12 times 11 times 10 all the way down to 1. But instead of 12, here, I'll put it up here, 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. And I'm not putting a 1 because it's not prime. But 12 is 2 times 2 times 3. 11 is prime. 10 is 2 times 5. And 9 is 3 times 3. 8 is 2, 2, 2. 7, 6 is 3 times 2. 5, 4 is 2 times 2. And then 3, and then 2. And what this question's really asking, like ultimately what's asking, is if I put 12 factorial and I think of it again as this like long string of beads, how many 3s are there? Okay. And there's a method for teaching this that I usually get into like in my second or third lesson. And people sometimes go like 12 divided by 3, it's 4. But as you can see, there's 1, 2, 3, 4, 5. And it's because all the multiples of 3, all the multiples of 3 are going to have a 3. Okay. But 9 has 2 3s. Okay. And 27 has 3 3s. And 81 has 4 3s. And 27 times 2 has 27 times 2, the number 54. Okay. That's going to be 3 times 3 times 3 times 2. And 27 times 3 is 81. 81. So a lot of times these numbers, this is like in the first couple of lessons, I have my students memorize certain, you need to know up to like 3 to the 5th. That's the edge of the universe, not 3 to the 6th. And I have a student who recently did something like 3 to the 8th. And they were doing something like 3 to the 8th minus 2 to the 8th. And they tried to figure out this number. And I'm like, I told you that you didn't have to memorize that one. 2 to the 8th, they do have to know. But that was not the way to do it. For anyone wondering, you're supposed to factor it using a difference of squares. But that's like lesson 3 or 4. Okay, so that's algebra and getting into linear equations. So like something like when this question saying 1,000 factorial is divided by 10 to the n, I'm not going to be looking for tens because tens will not exist. There's no 10 is not a prime number. I really care about how many twos there are and how many fives there are. And the truth is, I really care about how many fives there are because there's always going to be way too many twos. Look at this caterpillar again and look at two. Two is yellow and there's yellow everywhere. Okay. Every other number has at least one, okay? And then there's numbers like 8 that have 3 and 16 that have 4. And then 32 has 5 and 64 has 6. 96 has 5. So the thing is, twos are rising exponentially, you guys. That's what the word means. Like there are so many twos. That yellow color got used 97 times. That's the thing. You got 97 times on this sheet. But fives got used 24 times. Fives got used for every multiple of 5. 5 times 20 is 100. So it was used for all the multiples. And then there were 4 other numbers here that had an extra 5, like 25 and 50 had another one, and 75 and 100. Okay, so 4 more. So that's, these are like these number property problems. And as I said, it's all about factoring and like these patterns. I don't know if like some people are overwhelmed, but I think I'm just trying to show you that like this is why I teach this number caterpillar stuff and why I want you to get so familiar. You like know these numbers, you get to know them really and pick which ones you like and don't like. And you start seeing like how some numbers are related to others. And as like you start seeing things in like in colors in 3D, and it becomes a lot easier to process this like overwhelming information. And anyway, that's the end of it. Okay. If you're still here, bravo. I hope you liked it. I'll put some of this other Leland stuff here. Let me see. This is my this is my name. This is my QR code. If you want to find me, if you want to schedule a intro session, I would, be happy to meet you and talk with you and try to give you some advice on what your best course of action is. And and thank you so much for attending. I really appreciate it. Hope you guys liked it. The answer to the last problem, the answer to the last problem, gosh, I should have done that. The answer to the last problem was 1, 2, 3, 4, 5. Yes, by the way, yes. The answer was 5. Sorry about that. Yes, Alexander, yes, very good. That was good. I see that. Okay. So, cool. Okay, yeah, very good. Okay. Anyway, again, so Izzy, you still here? I think I'm supposed to pass this off, but I think you guys got all the tricks. And then let me see if I still have that thing up.